Good afternoon and welcome to this NZIOB webinar. My name is Malcolm Fleming, the Chief Executive of the New Zealand Institute of Building. A special welcome today to Keystone Trust students who I understand are joining the webinar in good numbers today. So on today's webinar, we'll be covering both the XFrame product that Jed Finch has developed, as well as the journey that Jed has taken from the time he applied for NZIOB Charitable Education Trust funding back in 2017, at a time that he was completing a Master of Science degree at Victoria University School of Architecture. His application to the Trust back in 2017 read, the research thesis examines how we can design housing in New Zealand that will not produce waste at the time of its life cycle. The eventual aim is to produce buildings that are designed to be disassembled and whose parts can be on-sold and recycled. Jed was successful back in 2017 in getting funding from the NZIOB Charitable Education Trust, which allowed him to go on and create a product that has now been taken to market, which therefore delivers on those high aims that he set himself back in 2017, his research proposal. With Jed's strong connection to the NZIOB Charitable Education Trust, I will shortly pass over to the Trust Chair, Graham Stanlich, who will provide an overview of the Trust's activities and proposals for 2022. Graham will then introduce Jed, and I will rejoin the webinar at the question time component of the session. So for readiness for that, please submit your questions through the platform tools, which I will then moderate when I come back on at the end of the session. I'll now hand over to Graham.
Thank you, Malcolm. And thank you very much for the opportunity to talk a little bit more about the Trust and just perhaps reinforce just what we've been up to over the last few months in respect of Trust activities. Just a little bit of background to the Trust. The purpose of the Charitable Education Trust is really to further the objectives of the New Zealand Institute of Building by promoting and supporting the education and training of its members or members of the building industry, awarding scholarships and prizes and providing grants or other financial support to members of the industry, and then to provide other such support to assist in the advancement of education and training of industry members. The Charitable Education Trust is a recent amalgamation between the NZIOB's two former trusts, the NZIOB Charitable Trust and the NZIOB Southern Chapter Education Trust, and now encompasses the whole of New Zealand under the one banner. This merger blends the former trust's slightly differing focuses and going forward allows the promotion of construction industry research and initiatives in conjunction with the development of opportunities for those with trade qualifications to undertake ongoing study. Now, along with this new national coverage, the Trust also has a greater quantum of annual gifting to undertake, all of which leads to a wider distribution of funding, both geographically and in terms of the proposal types for which the Trust provides funding opportunities. We currently have 8 trustees across the country. We have 3 in Christchurch, in Graham Goss, Samir Govind and Andrew Marshall, 2 in Wellington, being Sean McGuinness and Guy Cassidy, and 3 in Auckland, being Graham Birkhead, Phil Brosnan and myself. In the 4th quarter of 2021, this new trust will launch its new programme of scholarships and prizes and grants, coupled with some events planned over the spring and summer periods. We have had some industry events planned recently, but are currently rescheduling those in light of recent alert level changes. But don't worry, we'll be out with more information on that very soon. So we welcome Jed Finch to come and have a chat with us today and to tell us what how he's benefited from his award in 2017. When the Charitable Trust awarded Jed, who at that time was a Master of Architecture student at Victoria University, $10,000 grant towards his research in waste-free buildings. Jed used the money to build a large-scale and widely publicised circular economy pavilion at Victoria University to test his research outcomes. This pavilion used a unique diagrid framing that can be used for flooring, roofing and wall elements, such that it can be deconstructed and rebuilt many times. And the pavilion that Jed built with funding from the NZIOB Charitable Trust received international acclaim and was widely publicised in mainstream media. Furthermore, it was recognised as helping to better educate members of the public regarding end-of-life waste issues associated with buildings. The product that was at the end of his research, XFrame, has successfully raised a significant seed capital to advance the delivery of the product through New Zealand and Australia. And the development of the product is now taking off and is currently planned to be showcased at the Australian Institute of Building event following this presentation today. Jed is a great example of one who has utilised the Charitable Trust's awards programme to develop a product that has the ability to create industry betterment, and the Trust looks forward to many more such successes with future recipients of its awards. So Jed's now going to share his learnings with us, and I'll pass over to Jed to take us through his presentation. Thank you.
Thanks, Graham. Welcome, everyone. Thanks very much to the NZIOB for having me here today, and thanks for tuning in. I'm going to go through, first of all, just a little bit of background about what motivated the initial concept, the initial ideas behind XFrame, and then go through the research and development process. So obviously, the environmental impact that the construction industry has on the environment has become more and more publicised and more understood in recent years. And it's perhaps a key pillar of many new projects is how they deal with the impact that they have on the environment. So construction is one of the largest consumers of raw materials. It's also the largest producer of solid waste. In New Zealand, we've got very good at managing waste at the time of construction. So we have different ways of sorting those materials, but what remains a problem is waste at end of life. 30% of all waste to landfill in New Zealand is from the renovation and demolition of buildings. So the end of life building material management process is a huge contributor to our waste. And that's simply because the buildings aren't designed for change. It's a very well understood sort of premise in the construction industry. If you're going to make changes to the building, you are going to generate waste. The materials and the way those materials were put together when the building was built doesn't mean that it's makes it easy to take apart. And the alarming issue about this is that it's a factor that continues to grow alongside the growth of the construction sector. So you can see, if you follow this blue line, which is the volume of waste that the construction industry is producing, you can see in 2008, it actually dips. And that's because obviously financial crisis. So construction projects are decreasing. There's less projects on the go. So there's less waste getting created, less demolition happening. But as we start to inject into our economy and as we start to grow again, the construction waste just grows and grows and grows. And I haven't got more recent statistics than this, but we could expect based on the construction behavior of the current market that this figure has gone sort of off the chart, which is really alarming. In 2005, we set goals of reducing waste to landfill by 50%, and trends like this show that we've failed essentially to meet those goals, and so that the changes that we need to make to the industry are even more critical today. So again, why is that happening? It's a result of the way we build. We prioritize the economic imperatives of construction: fast, cost-effective materials that are abundant. They were abundant, obviously, before we've had issues. And then we don't worry about so much that the end of life. We try and build for maximum durability. We build for as long as possible. And then when changes do need to be made, we relegate those to someone else's problem. And so this is the common end of our building products is simply landfill. So we know very clearly what the challenges are. We know what's wrong. We know that the way we build is having an impact on what happens at end of life and how recyclable those materials are. We know that the fixing methods, the adhesives, the chemicals, the modified materials that we use are causing these problems. And to some extent, we do know what we need to do. We need to change those fixing methodologies. We need to update those materials. We need to design for the end of life. But like I mentioned, we're responsible to the economic forces of the market. It's very difficult to have a customer who is willing to engage in investing in some of these technologies because that end of life issue is so far away. It seems so distant from the conception of the building. So the solution, and something you should have heard about now a little bit more often, hopefully, is this idea of the circular economy. The circular economy is what would be suggested a solution to this problem. It's a framework of ideas and of concepts that say, well, what happens at end of life should actually be designed from the start, and that should allow us to better utilize those materials. The ideas of circularity are basically common sense. You want to design a product so that by the time it gets to the stage where it's no longer useful to that person, it can then be in as much utility as possible reused. So the smallest loop here, the reuse loop, is the priority loop. We want to take the product and its whole integrity without having to mush it up and remanufacture it or reprocess it or clean it up. You want to be able to use it directly. That's the most attractive reuse and most environmentally effective way to recover a product at end of life. Obviously, direct reuse isn't always feasible, and so you have to go back to things like remanufacturing, refurbishing, and even recycling. Recycling in this sort of sense is actually viewed as a last resort. We don't want to have to take something right back to that energy input, that material input stage. We want to be able to reutilize these products as whole entities. And so, housing in general, or construction in general, is actually very good at that. We do a lot of refurb, we do a lot of looking after our buildings so that they last a very long time. But regardless of that, we do need to consider the end of life, simply because materials are just buildings are such a large consumer of materials. We don't really have a choice. And there's a lot of guidance for you about how to go and do this. So if there's any architects or designers or people that are dealing in the design of infrastructure, there's this list of well-known, there's 14 points here of how to design a building, how to design an infrastructure system to be more friendly to end-of-life recovery and reuse when that time comes. This webinar is being recorded, so you'll be able to jump back to this list. But these ideas have been around for quite a long time. You see Philip Crowther's an Australian architect who an academic who came up with this in the late 90s, and then it's been expanded since then. These are all, again, it's fairly self-explanatory stuff, but what it does mean is it asks you to reconsider the cycles of a house or the cycles of a building, right? Often the structure of that building will be the thing that lasts the longest, and all of the other things inside and around that building are changing. You replace the roof, you move a wall, you move a window, you might add a room, you might take away a section of the house. All these things change. And so this is a piece of work that was done way back in 1994, where we looked at, okay, how could a building be set into temporal layers or layers of time to say that, okay, well, the stuff inside the house is probably going to have only a 2.5-year cycle. The space plan, so things like the internal partition walls, they might have a 10-year cycle, which makes sense if you look at commercial office space. The services, okay, well, maybe after 25 years, I'm going to have to replace some of the plumbing. And then the structure, perhaps in that 80-year period, I'm going to have to do major structural changes, whether that's refurb, upgrade, strengthening, all that sort of stuff. And the skin, obviously the cladding layers sit somewhere in between that. And that's relevant here in New Zealand. That skin layer sort of reflects the 50-year specification we would expect cladding products and those weatherproofing products to last. So that's a really simple diagram to understand how we need to design things over a series of layers. The structure is going to be the longest cycle, but these other layers are almost should be prioritized to say we need to address these issues because they're changed more often. And the reason why the circular economy approach is so effective at managing waste is because it's a top of the cliff solution, right? It doesn't say, oh, we've got all this waste product, how do we now manage it? It's saying, we're starting off with the building. How do we make sure that that building then does all of these things at the end of its life? And because of that, it has downstream and upstream implications. Downstream saying you don't get the waste at the end of life. Upstream saying when you get to end of life, you no longer need to actually get new materials. You don't need to pull out more minerals, more materials from the earth. You can recover these materials, reuse them, and that actually allows you to create new buildings without having more negative effects on the environment. So that upstream, downstream benefit on the environment is really promising for the circular economy. And just before I jump onto the XFrame R&D stuff, I just want to point out that there is some excellent international work that's been done in this space. This is the Loblolly House by Kieran Timblake Architecture. It's a beautiful building built with Bosch Rexroth aluminium framing. So the machine frames that you'd see in production lines or in machine rooms or in manufacturing, they took this standardized product and they applied it to the sector, and they applied it to a house in particular to produce this wonderfully spacious home. It's beautiful, raised up, it's in a tidal area. And everything about this was designed to be demountable. So it was all based on these standardized grids that then these elements could come into. And the cladding elements were built as cassettes that actually bolted onto the frame from the outside. So if you wanted to, you could get in there and remove one of those cassettes, and your frame and your floor and everything, all of the structure would maintain its integrity, but you could very easily change what's plugging into it. Obviously, there's a bit of an aesthetic implication, right? There's a bit of a exposed aluminium framing inside your house might not be something that you're after. The cross bracing might not be something that you're after. But as a first cut at what a circular economy building could look like, this is an excellent example. And Kieran Timblake continue to do great work in this space. This is a much more recent one. This was made in Switzerland in 2016 by McDonough and Partners, a firm out of the US. So McDonough is interesting because he wrote a book about cradle to cradle design and about how we should be designing all our products and all our systems to be recyclable. And then he said, okay, well, now I need to go and prove and validate all my ideas. And this was his version of that. So what makes this building really interesting is it's actually only made up of three structural elements. So you've got a straight piece, an angled piece, and a corner piece. And all of these bolt together to form a diagrid, aluminium diagrid in this case, that's a space frame. So the space frame basically means it's a multi-depth structure, and that means that you can get the horizontal spanning that you need while also having this really sort of small module that's easily handleable and very easily adaptable. It's one of the key things of circular design. You want to be able to use the same bit everywhere as much as possible. So a wonderful building and very sort of out there in terms of this is a whole new way of going about designing a building envelope. What this product here is a high performance polyester sheet product that has a gel embedded in the corrugates that has compressed air injected into it. And so what you're actually getting is effectively an R3 wall in 10 millimeters of film. So this was done deliberately. It was trying to provoke the industry to say, well, actually, we should be able to look at the technical materials that we have, the plastics, the metals, and say, well, if we design these effectively, they can be used to great environmental effect. You know, this 10 millimeter layer is the internal lining, it's the external cladding, it's the insulation, it does everything. It's the air tightness layer. It's also obviously really durable. The argument that they made was that this would be recyclable because it's a high performance polyester product, and that the gel could be drained out and everything could be ground up and turned back into the same polyester sheet product. Obviously, that requires a certain amount of infrastructure to do that, and it requires a large volume of that product to make it environmentally sort of sensible. So you can look at those projects and you can quite often, quite easily evaluate some. They look bloody expensive, and yes, they are expensive. They look carbon intensive, and yes, they are using a lot of metal. They're using a lot of specialist technology. They do have issues around some thermal things and air tightness, and that relates to the Loblolly one. And they use these materials that are, just not off-the-shelf products that we couldn't see adopted in the industry very quickly. But they do, on the flip side of that, they have a lot of advantages. They take ideas of dry jointing, so joints that don't require any adhesives or glues that can clip together and be reused over and over again. So there's some really good aspects to those projects. When I looked at all this work back in 2017, I was interested in how we could take this principle of a modulated structure, but apply that to a material that is much more readily available and a manufacturing process that's much more readily available. So I'm just gonna, there should be a video here, but it's disappeared. That's all right. This was the outcome of that first initial idea of what XFrame could be. So in mid 2017, come up with a very small scale desk sized model of this system using a laser cutter and MDF sheets, and then used the opportunity of applying to the NZIOB Charitable Trust to say, how would we validate that this little wooden model that I've got on my desk could be scaled up to create a building system that was actually sort of representation of what might happen in real life. And you can see that this prototype kind of starts to test some of those things. So we've got, for example, the floor structure, the wall structure, and the roof structure. So testing if the same module and the same parts can form all of the building. Testing if the system can span, not just span, but also cantilever. So it was a bit of a test to say, okay, well, you know, quite often in buildings, you want to be able to do more than just a box. What else would that box be? And so things like openings are considered, junctions, intersections, that sort of stuff was included in this prototype. It was based on a 900 millimeter module. The rationale behind that was that it's about the right size for a door. It's also quite an efficient module when we manufacture the XFrame product in this variant. And obviously, although it looks sort of complicated and scary, the principle behind it was that when you went to line it, when you went to enclose it, you'd actually only need two different shapes. You'd need a square for the middle and you need a triangle for the edge. And that would be able to be arrayed right across the building. So that was prototype one. And again, we used the NZIOB Charitable Trust funding to get this off the ground and to get this built. We're supported generously by Makers of Architecture and Carl Harvey to get this one off the ground. And it generated a great deal of interest. But what it essentially did is probably ask a lot more questions than it answered. The wall structure here was through sort of 230 millimeters deep. So it's a really chunky wall. And because of that, it was extremely expensive. It was using a lot of material to do not much structure. The other implication of that is you can see there's bolts everywhere. There's more than 1,000 bolts in the structure, which I'm sure builders on the stream will, now they don't want to be putting bolts in all day. It's not something that's really, although it's, easy to do, you do a lot of it, you get very tired of it very quickly. So we needed to come up with a way that could do away with some of this dependent fixings and simplify the system. So basically a series of areas to work on and to develop further. Think about how to make it more economical, how to look at these different wall framing thicknesses and make them more align with conventional thicknesses, and of course also understand the structural implications of this, further making it more relative and more useful for the building industry. This was the next prototype major, so the next big prototype that we built, prototype number 13. This was done in a workshop in Auckland in May 2019. You can see straight away that the structure's been what I call rationalized. It's been simplified greatly. So we've taken out a lot of the complexity. We've slimmed it down. We've done a lot of engineering analysis to understand what material do we need and where best is it to use things like bolts? Where best can we utilize metal elements versus timber elements? How's the load transfer working? You'll notice we've still got it working in the vertical axis, the wall, and in the horizontal plane in the roof structure. This was a great little project just to test how it would work in a very controlled environment again. So it's useful as office partitioning, it's useful as workshop partitioning, but we're not having to deal with all of those other layers yet. One of the key things to point out is the reason for this braced structure is that it means that you can create a frame in which it doesn't rely on the lining materials to brace that and to provide the additional structural integrity that it would need, particularly in an earthquake zone like New Zealand. So the X brace gives it that structural integrity. The flow-on effect of that, it means that we create a structure that has essentially an infinitely scalable fixing grid that we know precisely where those fixing points are. So each of these plates you can see has a little hole mounted or routed in it. That allows us to also prefabricate lining systems that can just clip on and off that grid, because we know precisely where all those fixing points are. And so not just separating that plasterboard layer, but now we can actually change the way that layer fixes to the wall. So we can create little reversible clips that mount these linings that can be easily pulled off and on. And as we go through this, I'll show you more what that looks like. So this was the manufacturing process. Obviously, CNC routing. The advantage of routing is that it's an established technology that's pretty much in every town in New Zealand, because it's used to build furniture, cabinetry, and kitchens. Lots of the furniture and joinery shops that have existed in small town New Zealand and right throughout the country have brought into this technology. It's not a technology that has a high threshold of entry. And because of this, we can take advantage of that. This is a CNC router cutting XFrame at Unitec in Auckland. One of the other prototypes we did was in Central Otago in Alexandra, where I grew up. And we just went to the local joiner and said, look, can you help us out? We want to cut this building out. It was just before Christmas. They had some space. We ran the router through the weekend and no issues at all. So having access to this manufacturing technology is not difficult. And on the right there, you can see the cut parts. This was the next prototype, and we'd done a series of structural tests in between this. We'd done a series of frame and module tests. This was the first, okay, let's get it outside, let's get it on site, and let's see actually what happens. Because as many of you know, translating something from the controlled, confined space of an internal partitioning system or an internal pavilion and then taking it to site just asks so much more questions of the system. So this was done and supported by a guy I met who basically just wanted to take a stab at the technology and have a go and get hands-on and help build it. It was done, in another one in Auckland, this one in Ardmore, just south of Auckland, as a 10 square meter cabin unit. And here you can see again, X-frame floor, wall, roof. We've now experimented with how would we locate a window in that geometry. Here we're just maintaining a standard window size to fit within the module. And you can see the starting development of cladding and lining systems. And so this was the first cut at the cladding, and I'll be the first to admit it's not the best solution, but it was where we were at back at the time, which was 2019. It was a thermally modified plywood product. So Abodo supported us with that, and we worked with them to come up with this diamond shingle cladding system. So the reason for this shingle system is it means that you inherently introduce an overlap into the panel joint that's quite a lot larger than a traditional timber panel overlap. And what that gives you is basically more durability, more resilience of the sheet product, because the geometry is doing the waterproofing. You're not relying on any sealing or painting or any other adhesives to seal off, or silicons to seal off the cladding system. And of course, we're using a structural cavity batten. So what that means is that the structural cavity batten, that 45 millimeter square piece of timber, is bolted into the X-frame grid, again, because we know where that is. And then we can fix into that cavity batten so that you have a series of layers that are all easily separatable. It's not really a word, but can be easily separated at end of life as needed. For me, as an architect, as a very young architecture graduate, learning about all of these flashing systems and the implications of introducing cavity systems and roof overhangs, pitches, all that sort of stuff sort of got addressed and questioned in this prototype, which was really good. A beautiful finish and sort of just a testament to the innovation that Abodo has brought to the sector. Again, the thermally modified wood fits so nicely into the circular economy design agenda, let's call it, because it does away with all of those chemicals, right? There is no copper chrome arsenate. There is no light organic solvents in the treatment. It is you're basically exploiting the natural advantages of timber, and you're enhancing those through the thermal modification process. a front view of that process. So we did the shingles on the outside, and then we did a sheets on the inside cut. It was some recycled windows and doors that we'd managed to find off Trade Me. It was all done on a bit of a thin budget, but it was really well supported by the sector, and we wouldn't have got anywhere without this first prototype. This whole circular economy thinking wasn't just limited to the outside. Like I said, it was all about that complete wall build-up. And so here is the internal lining, and I understand this isn't for everyone, and we have moved away from this, but this is a 12 millimeter plywood sheet clipped to the wall using the fast mount reversible pressure clip system. So the fast mount system was designed originally for the yachting sector and for the luxury liner sector. But what Fast Mount does, and it's a New Zealand company, which is excellent, is they've brought it to the construction sector. All it is a male-female clip system that has a sort of a bobble clip on the back of the panel, and then a female clip in the wall that can be routed, or the holes for those clips in the appropriate sizes can be pre-routed into the locking plates. And then you can just simply put those clips in the two pieces and push the linings on. And so again, we can do all of the linings in this whole space with this clip system. You can see the floor system is bolted in just like the first prototype. In the wall there's a Terralana insulation product, so a wall blend insulation. Insulations in terms of the circular economy is a complex area, because you need to look at, okay, well, what is the capacity of that material to be directly reused? What insulation product actually has the longest shelf life? What stays fluffy, doesn't slump, rejects moisture and mold, and will actually last the longest? So the Terralana product's a great example for that. What Terralana also does, and the polyester wool blend product does, is it's very good at dealing with moisture changes in the wall. So if you're designing a high performance building today, quite often you'll be installing a vapor permeable internal membrane that's one directional, basically that creates an internal airtight layer that allows vapor to pass through it if needed. What this building does is put that vapor layer on the outside and allows the insulation, or the wall blend insulation, can actually deal with that moisture change and soak up and release that moisture as the humidity changes. So a lot of complex building science going into this wall, but basically what I'm saying is that together with these technologies, we can create this circular economy wall system using off-the-shelf products. A whole lot of failures and mistakes and things that just did not work, as I'm sure you can all imagine on a prototype project of this. Of course, this was in Auckland, so it just rained and rained and rained and rained, and so plywood plates buckled and bowed, and things didn't go to plan. We had issues with how the deck was built. We had issues with how the cladding system was joint on, and some screw details around that. You can see the windows are still framed out by hand. And of course, there's building wrap everywhere. So there's so much work to be done. But it was a great way just to get out there, fail quickly, figure out what didn't work, and move on to the next stage. And the next stage of this was a bit of a sort of... well, it was a trip down to the South Island, but it was basically ask my parents, would they support me to do a prototype? We needed another one. And they were the ones that were willing to help, which was great. So this is another 10 square meter cabin unit, but here we're using a panelized XFrame system. So the major change is, rather than having to create whole wall elements, we're now able to create panels that are 1200 millimeters wide. They can be built in the shed. In this case, they are built on the deck. They were whacked together with a rubber mallet, and they're built, sort of brought over to site, stood up and bolted into place. And so that allows us to do a little bit more offsite assembly, allows the system to be a bit more easily deconstructible into sub-elements. So now we can go from walls to panels to parts. And all of these panels are now on a 600 millimeter grid, which is just obviously a lot more standard module and more sort of easily sort of adopted by the industry. On the right, you can see our efforts to take out the building wrap, basically. So this is a thermally modified plywood being used as a rigid air barrier. And And what's happening here is that that cavity band, which you can see that the bolt fixings for going vertically through it and horizontally where it's needed, that is being clamped to the building into a nut inside of the frame that's holding on a rubber gasket. So the rubber gasket is it doesn't have any adhesives on it. It's a bubble gasket. So it's got two parallel bubbles that are compressed. So as you tighten that cavity band onto the wall, it seals the joint in the rigid air barrier. So what that means is we don't need to tape the seam in that rigid air barrier. We can just clamp it on. Again, I have to highlight that this is a prototype. So you can see right beside that beautifully designed clamped element is tape. What we were looking for is a window system that had the foundations of a circular economy possibility. What we looked at and what we experimented with is the smart fit system. And so a limitation of smart fit is that it's not a thermally broken system, which is a problem given the increasing requirements for energy efficiency. However, what Smart Fit does well is that it face fixes to the outside of the building. So rather than fixing through the reveal or fixing from the inside, it fixes through a series of predefined holes in a flange that's on the outside of the building. So from an air tightness point of view and from a durability point of view, really good. What that means is that we could actually bolt the window into the flange in the XFrame panel, which again means you're not ripping nails out of reveals, trying to get the window out, having to cut things and making a mess. You're unbolting those bolts and pulling the whole window out in one set. However, obviously to comply with the code and regulations around how this window should be installed, we need to seal over that fixing. And so that's the Smart Fit tape. So perhaps in the future, there would be a gasket option or some sort of alternative sealing specification that we could use for that. Just to give you an understanding of how this all works. So again, CNC manufacturing on the left. This is the unit at the University in Wellington. We then take those parts, we arrange those parts. You don't have to do this. In fact, the most efficient way to build the panels is to go from the router directly into the panel. And we've created a workflow that allows you to basically cut a sheet of plywood and turn it into a panel. You assemble that panel, like the third picture there, and then you put those panels together to form a building. And actually the time lag over that whole process isn't very long. Providing you can get hold of plywood, which I'm sure everyone can relate is somewhat difficult at the moment. You can actually have a 12-day turnaround on a project like that. Obviously, the bigger the project, the longer the manufacturing takes, but we can also drip feed panels and panels, that sort of stuff. So there is this ability to scale, and obviously this is one router. So as soon as you get multiple routers in, you're sort of spreading horizontally across your manufacturing capability and increasing production rates. The other nice thing about this is a router takes about 35 to 40 minutes to cut a sheet of X-frame. And so you can have one person operating 2 or 3 machines, because that person just needs to load up the machine, wait for it to cut, unload it, and load the next sheet. And in quite a lot of instances, the sheet loading is actually happening automatically. So all that person is doing is just checking everything's in the right place and the machine's doing the right thing. What you can also do is have that person assembling panels. So there's a whole sort of production workflow that fits into that. This is the finished prototype down in the South Island. Here we've got straw board, which is a reconstituted waste product. Plytech New Zealand has now started bringing this in. It's a low emissions board product that uses agricultural waste. Here we've bolted it to the wall and used little black headed hex nuts to bolt into the XFrame grid system, just to create a really sort of, it's quite an industrial vibe. But what we wanted to demonstrate here is that you could use whole sheets if you wanted to, and you could use a more ecological product if you wanted to on those internal linings. The same, the door unit at the front here is a smart fit system, and the cladding in that case is also the Abodo thermally modified sheet product. So this prototype was good because it did allow us to achieve the material recovery that we wanted. The changes to the cladding interfaces and the building wrap layer to create a rigid air barrier allowed us to get these recovery rates. And we are sequestering a lot of carbon because of that whole timber buildup, because of the local supply chain. Less fixings, no nails, very few screws, some screws in the cladding, and obviously screws in the timber cladding as well. The next step was a bit of a jump. We had some interest from some guys in Australia to see if this XFrame technology could be used in a different context. And what's interesting about Australia is it has a different consenting model. One of the challenges I'm sure you can imagine that you'd face in New Zealand with a technology like this is that getting it through building consent can be very difficult without precedent. And so in Australia, they have a privatized consenting model in some states and in some instances. And what that allows us to do is work with one of the consenting agencies to say, well, how would we get this through? And they have obviously a vested interest in executing on that because they want to turn around the consent. And so you end up with a very collaborative environment, which allows you to bring across more innovative technologies to the sector. So that's the reason why this took place in Australia. And it was a slightly scaled up because obviously we could get a building consent. This was built during our first lockdown. So it was just sort of end of first lockdown last year. So June, July, manufacturing and fabrication and assembly in Australia, all built using a big set of instructions that looked exactly like this. The overall panel structure, breaking the panels down into their actual structural build-up. And then here was the first photo I got, which was, as you can imagine, not being able to travel was pretty scary, but it looked like they knew what they were doing, which I was genuinely surprised, but they managed to put it together. 4 blokes spent the day putting all the roof wall panels together. Here you can see we opted for a conventional floor structure. That was just to simplify the scope and to give them a good shot at getting the walls right. Here you can see a few changes to the system. So more structural simplifications and optimizations. And most importantly, now we're developing a way of creating any possible geometry using the XFrame system. So you can see that the top of the wall is a raked wall. And that raked wall structure is created all out of XFrame components. So that means that we can achieve sort of 90% standardization of a wall, and that 10% customization can come from XFrame, just different members. And so what that means is that you could actually just pull those 6 or 7 pieces off the top of the panel, make some changes to that, and you'd have a standard panel without having to rearrange any of the other components. This was also the first time that we'd really dealt with sort of a full engineering scope, in the sense that we had to validate this for building consent. We also had to provide efficient documentation for energy efficiency, articulation of services, all these aspects that are obviously integral to delivering a built product. There were some sacrifices. You can see in the middle here, there's actually a 90 by 45 piece of timber. It's painted white. I'm not sure why, but it's running straight through the middle of the frame system. The reason we did that is we needed a fixing interface for the corners. We needed to be able to basically coach screw into that. That's since been modified, but again, a prototyping phase was a way of addressing that. Obviously, it's not what you want to do, right? Because you just end up with more material rather than less. And here you can see the advantage of the system is that there's holes everywhere for running surfaces. It's very easy to articulate them. The corner you can see is actually recessed from the structural corner, which allows you to run surfaces around the corner very easily. And here's the internal lining process. I apologize for the quality of these images. These are just screenshots from the video, but you can see fully insulated structure, a shadow gap plywood that's completely routed in the factory and brought to site and clipped on, allows you to get these beautiful high quality finishes, very, very accurate and very quickly. And here's the guys just press fitting those sheets into place. So XFrame Series 5, we called that one. That we basically had a series of structural tests done that allowed us to validate the bracing unit of the system. We could get a very effective unlined bracing component. We had a much better understanding of cost. You can see that there, so it's about $75 to $88 per square meter, based on a rate of $100 an hour to manufacture something like that. Very rapid assembly time, and this was for people that hadn't used the system before. And then obviously that disassembly time, we disassemble that in sequences or in different parts to test that, and again we can get a very effective speed. So that was sort of the major prototyping phases up until middle of last year. Since then, we've gone out, as Graham mentioned, and got some seed funding. And what that does is change the nature of the work that we do. TRL stands for Technology Readiness Level, and the government basically has a 10-stage TRL. One is you've got an idea, but you don't have any evidence, and then you build up over that. So TRL 6, Technology Readiness Level 6, basically says you've got a series of validated prototypes, and now you need to validate them in real-world commercial instances. And so that's the prototypes that I'll show you now. The first level 6 project that we did was the first consented XFrame unit in New Zealand, which was really exciting. It was in the commercial office space. This is in an office building in Wellington, above Unity Books, 257 Willis Street. The client was outstanding on this project. They wanted a flexible co-working space, which could be changed over time as their requirements changed. XFrame was a great fit for this. And they wanted a very much looking industrial vibe to the product. So we went with that. These are a 12mm LDF board with pressure clips with a 1mm powder coated steel panel over the top of it, which essentially forms a floor to ceiling 8-meter long magnetic whiteboard, which is pretty cool. And it really matches the look that we're going for in the space. Just as a completely different aesthetic, here's a completed fit out in Tonsley in Adelaide, South Australia. Again, using an internal fit out lightweight version of the XFrame system, but going for a much more high-end professional look. Here's XFrame's general manager, Carsten. He's posing for the photographer, but basically just showing you the expressive modularity of the system, the real efficiency and elegance of the XFrame as a refined product here, where you can, you walk into these rooms and the people are sitting at their offices, and you just go over to the wall and you lever off one of the linings, and everyone turns around and looks at you, just wondering what on earth you're doing. And it's because of that optimization of those fixings that we can do that, and the fixing grid. This wall is 15 meters long, I believe, and it's a millimeter perfect from end to end because of the grid system, because of the way we're joining it together, which again allows us to achieve these really fine finishes and prefabricated linings. The other advantage of this, as you can imagine, there's no waste on site, there's no mess on site, there's no sawdust. That the only mess you get is if you have to drill into your concrete floor. Here's another completed fit out, and this was taking the system a bit further. So we were interested in how could we get a zero make good XFrame system deployed in an office situation. Obviously, in an office situation, XFrame makes a lot of sense. These spaces are changing every 5 to 10 years. Let's use the XFrame system to do that. What we've done is we've got a double-sided tape on the floor that can be peeled off to a primed concrete and a primed wood surface. And at the top, we've got basically it's a suspended ceiling lighting clip that affixes to the T-track. And you can see they're aligned to the T-track and intersecting T-track. What that means is you can unbolt that and there's no further fixing into the ceiling needed, which is really nice. It allows the person to make good that leased space very quickly. Obviously, you can see here also part height walls, different linings, skirtings, exposed ends, all sorts of other architectural details that are important. And this is the other side of XFrame. Obviously, I'm very much still passionate about how can this be used as a building technology for load-bearing structures. This is the major prototype that we've completed in Australia. This is a 50 square meter building, 4.8 meter stud, a large structure using 100 sheets of plywood. And we're very close to developing this further and taking them out to site. So a lot of R&D, as you can imagine, to get to this stage, and a lot of checking and engineering and sort of compliance to work through, but very exciting all the same. Next steps, I'm just going to show this as a bit of a teaser. We're working on an internal kit set product that will be purchasable online that you can just buy. Here's a little phone booth, but it'll be for everything from internal freestanding partition walls, meeting rooms, desks, cubicles, all sorts of stuff will be possible. And so that should be coming online early next year, all going well. Just a real quick summary, just for reference, that's the XFrame system. We take a locally grown timber, we turn it into a high value product, and we turn it into a high performance waste-free building. if you're interested in learning a bit more about this, here's some recommended reading and links. I'll share this with the team to link out. These are all URLs that you can click on. It's a couple of TED Talks there, and then some books about how circular economy can be applied for buildings. And I'd just like to thank the NZIOB hugely for getting this entire journey started, but also work of this nature doesn't come about without the support of a very open and receptive building industry. And so I think, if any of you are listening, thank you very much for the support that you've given us to date. A huge amount of work and generosity and expertise have been given to XFrame, and we're very grateful for that. Cool, that's everything from me. I look forward to some Q&A.
Thanks very much, Jed. That was great. Jed, I'm not sure that came through in the presentation, but you're currently a doctorate candidate now as well, ongoing with your studies. So, question from me is your thesis, your PhD thesis, is that a continuation of the topics that you started with your masters? And if so, how's it evolved, your research?
Yeah, the PhD side of things set out to really evaluate the idea that came about in the masters. It was to say, well, how would we really assess an XFrame technology? How would we evaluate if it is actually doing what it's saying on the lid? And so obviously there's been a bit of a splitting of resources. I've spent my time developing a way of assessing these buildings, and that's why I can be quite open about how they're working. And then the more commercial outputs are all about developing the technology and applying it to different sectors. Yeah, so there's sort of a multi-pronged approach to get where we are today. Yeah.
One of the first slides you came up with made the statistic about 30% of waste that goes to our landfills in New Zealand comes from the demolition stage of construction.
Yep.
So there's also a lot of waste that comes through from the construction side.
Yep.
Of the process as well, while we're building.
Yep.
And collectively, I think they come to a figure like half of our waste in New Zealand landfills comes from construction, like at the start.
Yep. Yep.
So how's XFrame dealing with minimising waste at that front end?
Front end, yeah. So good question. So you can sort of see, as we went through the presentation, you'll see the parts getting cut out on the sheets, and you'll see how they're optimized on those sheets so that they produce as little waste as possible. All of the parts are optimized across the width of a plywood sheet so that we can get exactly the number of parts that maximizes the sheet use. So that's the first area that we try and minimize the waste as much as possible. And then through the construction phase, obviously, because everything's a kit set, it's prefabricated, there shouldn't really be any waste on site unless it is a cut to measure element. Obviously, there's still realities. One thing that I've learned very recently is that when you do a commercial fit out, the concrete floor is never flat. And so we've started introducing a skirting board to our projects that have a 15mm overcut so that the builder can scribe those on site to compensate for the floor's waviness. So it's just learning things like that although we can actually create a kit of parts that will not have any waste on site, the reality is that the world isn't measured in the millimeters. It's far more complex than that, and so we need to be flexible to those changes.
Look, I've got some questions building up nicely, but before we get to those, which we all get to, I just had a question. You mentioned fast mount clipping system. You talk that coming across in the boat building industry, I think, yachting specifically.
Yep.
Are there so what other learnings can we take from other industries like boat building that can solve some of these ongoing issues that we have, particularly about weather tightness? Modular construction is another one. You're obviously doing some work in that space, but what other industries, and they're not confined to boat building, of course, have you been looking at, and which could start informing building practices?
Yeah, definitely. We've taken a huge amount of sort of influence from the industrial design, the furniture design, flat pack furniture, all of the fixings and methodologies for creating knockdown systems have been developed really well for furniture, for flat pack furniture, and we can borrow some of those. So we're using some of the dowel nuts and some of the insert nuts that would be common in that sector. Our reversible pressure clips obviously come from fast mount, and there's other types of clips that do similar things that sort of come from that furniture design end. And it's been exciting to try and introduce those into construction and see where they work and see where they don't.
Right, let's dig into some of these questions. I say there's a few of them. A couple of them were early on, and you covered in the presentation about penetrations. And I noticed you talked about penetrations, service for piping, etc.
Yep.
And one of the images you had was in a corner detail.
Yep.
Outside of corner details, how are you dealing with?
Yeah, so at every panel junction, the panel's basically two pieces of wood parallel, two pieces of plywood parallel, and then on each side of those there's a 45 millimeter vertical slot to articulate things like drain pipes and water pipes, and that's on all panel modules, and that can obviously then go horizontally or vertically through the panel coming up from that opening.
And the fire rating was another one that came up.
Yeah, I get that question all the time. Fire rating really depends on what linings you're using. And so for us, if you want to achieve a fire rated XFrame wall, you'd need to use a fire resistant lining product. That is like a plasterboard product. We're yet to find something that can be demountable and fireproof, but if you guys have ideas, I'm all ears and would love to talk. It's a really difficult area to address, particularly from a compliance point of view. Yeah.
Some of the questions came up early in and this is before you show those commercial installations. And the commercial ones I saw, Willow Street in Wellington and in Adelaide as well, and they're internal fit outs.
Yep.
So are the larger projects, are they confined to interior fit outs?
Not necessarily. So at the moment, obviously there's been a focus on the internal fit outs because they're much easier for us to work on. There's less complexity around them. But we are getting close to engaging some clients who are interested in housing, interested in much larger structures. We're excited about using the system in much larger office fit outs, multi-unit fit outs, inter-tenancy stuff, and really growing the system. Again, it's just sort of biting off little chunks at the moment to make sure we learn our lessons and don't get too carried away.
So one of the questions I had is, if you look at the XFrame website, it's Australian focused. If you're interested in using, looking at using XFrame on a project, contact us, and it looks like Australia based. And you touched on consenting and the collaborative model of consenting in Australia. Is the consenting model here in New Zealand restricting your ability to use XFrame?
I think, yeah, so the New Zealand sector is interesting because it's a performance-based code, which means in principle you could get XFrame through no trouble at all. The complexity that comes with it is that it's very expensive to get it through the code without upfront investment. And so the approach we have taken is that we can do a project in New Zealand, but it will cost you more because we have to basically get a producer statement for every XFrame project that we do in New Zealand, versus in Australia, we can roll out much more quickly sort of standards that allow the system to be used in generic installations. But yeah, the answer to that is in New Zealand, we can use the system. We'll just have to get a PS1, and then that will be the way that we get through council consent process. And the engineers are very happy to do that. And obviously it actually can speed up the consenting very well because you have a very sort of tightly controlled design package.
So on that same subject, just had one coming in, bracing capacity values for your standard panels.
Yeah. So it's 60 bracing units for an unlined panel, which we think is pretty good. Obviously, as soon as you put linings on it, it's going to go right up. That's for a per meter. All our panels are 1200. The other thing is we find that you actually 60 units is generally enough because you've got bracing everywhere. There's every element is braced. So you find that because it's so decentralized bracing, you don't have to worry as much about it. But of course, if you need more stiffness, then your sheet products are introduced and the fixing changes between those sheet products.
That's good, because that covers about 3 questions here all about bracing and seismic.
Yeah.
And this sort of touches on that the Australia New Zealand market. So how has the industry taken up the system? Are they keen to adopt it? Are they keen to trial it?
Yeah,
and are the experiences different on each side of the Tasman?
Very, very much so, and it really depends who you talk to. And I fully understand people's reluctance to use a system like this. Building anything is complex enough without introducing a new untested technology to that problem. We find that XFrame is more expensive than conventional construction, and because of that, it plays better in certain markets. And so the people that come to us that want something flexible, they're really excited about it. If I go to a mass home builder and say, oh, do you want to use XFrame? We're going to get told to go away. And I totally understand that. You know, they've got an optimized process. And so we need to get the product ready for that sort of scale. So basically, I'm saying that, you know, in its niche and good effective use cases, XFrame makes a lot of sense and people are excited to use it. But there is obviously the other side of that to say, you know, people are reluctant to take risks when they're having to lay down large amounts of money to build a house. It makes total sense.
We've got 1 minute to go, so we've exhausted the questions. Jed, thank you so much for your time. This has been a webinar we've been talking about for quite some time, and we last week thought, right, in lockdown, we've got an audience that is there for it. So thank you for that. Thanks, Graham, earlier for popping on also.
Very welcome.
Giving us an overview of the trust. And you are really a good an advertisement for what the NZIOB Charitable Education Trust is all about. So that's it from us. Thank you for attending the webinar. For NZIOB members, we'll be putting the webinar recording up on your member dashboards from this evening, so you can watch at your leisure. Thanks again. Have a good day, everybody. Go and listen to the podcast now. See you.
See you.